record first. Okay, it's recording already. Sorry. So yeah, it has a few resistors and a battery, and that has an EMF of 45 volts. So what you are required to find is at what rate this resistor, 20 ohm resistor, is melting ice. So initially this resistor is like inside a box, inside a block of ice at 0 degree. So you need to use a little bit of thermodynamics that you learned last semester. But yeah, it's very basic equation. So let's start. Okay, let me reduce this. And okay, let me do one thing. What I was trying to do was, okay, so you have this circuit. That's 20 ohm. There's another resistor, right? And there's another one. And you have another one here. And you have another one here. You also have a battery here. And you have another resistor here. Okay, so let me level them. So it's 20 ohm, which is inside a block of ice. This is 10 ohm. This is 20 ohm. This is 45 volts. This is positive. This is negative. 10 ohm, 5, and this is 15. So this is ice at 0 degrees centigrade. Okay, now what you need to do is you need to calculate the rate at which this ice melts. So that means you need to calculate the power that's being delivered here. Okay. So how to solve this problem? So to find power, so power is in a resistance, it's given by V square over R, or there's I square times R. Okay, so basically you'll need either the voltage drop across this resistor or current. So usually I follow the second one, I go for current and find the power. So here you have a EMF. So at first, let's reduce this circuit. So reduce this circuit to something like this. Whenever you have like a EMF and a bunch of resistor, you can do, what you can do is you can reduce the circuit into a basic circuit. So we can reduce this circuit into this kind of circuit where you have like a 45 volt EMF and you have a equivalent resistance. So you'll calculate the equivalent resistance of all of this part here. So let's do that. So here we have like a current coming out of here. There's I, okay, and it gets divided into 3 parts, like, okay, and then that current again comes back and joins at this junction. So it's a Kirchhoff's law. So Kirchhoff's law says that whenever you have a current that's flowing and there are branches, then the current will just divide into the components, and it's just a sum. It's like a normal sum, like it's I1, I2, I3. You can just add up to find the total current I. So this I, this will also be the I. This also I. Okay. So whenever there is like a division of current, that means that your circuit is in parallel. So here the current is dividing. That means these 3 components are in parallel. And here, if you look at these resistors, 15 ohm, 5 ohm, and 10 ohm, the current isn't dividing. There isn't any junction, so it's in series. Okay, that's how you identify whether the circuit, whether the resistors are in parallel or not. It's like if the current is being divided, then that means these resistors, they are in parallel. If not, then they're series. There's a basic thing. So let's find the equivalent resistance. So R equivalent here will be, you'll need to add all these resistance, 15 ohm plus 5 ohm. Let's add the series one, because in series you just add the resistance, right? And for the parallel ones, I'll just write it like 1 over 1 over 20 ohm plus 1 over 10 ohm plus 1 over 20. So how I'm getting this part? So whenever you have like a 3 resistance, like this one, and let's suppose this one, all of these are in parallel, right? R1, R2, R3. You have your equivalent resistance. 1 by R equivalent will be 1 by R1 plus 1 by R2 plus 1 over 1, 3. So that's, if you do the cross multiplication, you don't need to do cross multiplication. No, what you can do is just reverse everything. So R equivalent will be just reversing this whole, will be 1 by R1, 1 over R2 plus 1 over R3. So yeah, so this is your equivalent resistance. So that's why for the parallel one, I'm doing something like this in here, okay? So if you do this, the sum of the resistors in series is 30 ohm, okay? And if you do this calculation in your calculator, it's 5 ohm. So overall, you have a 35 ohms of equivalent resistance. So now your circuit is reduced into this, okay? So when I'm reducing this circuit, I'm trying to find this current first, right? This total current that's flowing in the circuit, so that I can later on find the potential across this parallel circuit. And if somehow I can find the potential drop across 20 ohm resistor, then I can find power. Or if I can find the potential, I can find the current flowing here, and I can find the current. So let's label it, and let's say it's I1, this is I2, this is I3, okay? So, okay. So now I have the equivalent resistance, now find the current. So current in this case will be, just use the Ohm's law, that is V equivalent is I times R equivalent, okay? So V equivalent in this case is the EMF of the battery, and I times R equivalent, okay? And your I will be E over R equivalent. So that is 45 volts divided by R equivalent is 35 ohms. So that's about 1.286 amperes. Okay, so that's your current. Let me put it in a box because we'll need that later on. Okay, now we have found the current. What we can do is we can find the potential drop only in this parallel circuit. So remember, in parallel circuits, whenever you have resistors in parallel, you have like a potential drop equal across all these resistors. In series, you have like power drop across here different from this, and this one different from this, because these are different resistors and the potential drop is different. But in parallel, no matter how big your resistor is or how small it is, the potential drop will always be the same, okay? So that means, like, if I only look at this segment, I only look at this small segment, that is 20 ohms, 10, and this is 20 again. If I only look at this, then the potential drop across this thing, let's suppose there's V, okay, that is going to be like the equivalent circuit of this, that is R equivalent let me write it R equivalent prime, because it is different from this one, because this R equivalent contains these series resistors as well. But now I'm only writing it for the parallel resistors. And you know that R prime equivalent, that is the equivalent of these 3 resistor, is 5 ohms, because you found it here. This was, right? This was 5 ohms. Okay, so now you have the resistance. Now what is the potential drop here? So that's the only, so potential drop at parallel resistors. It's going to be V, that is VA, that's equals R, yeah, I, because remember, even though there is like a division in current in here, when you like make an equivalent circuit, it's only like it's like a, you know, a single resistor with I amount of current flowing through it. So you have like I that you calculated in the first part, okay, times the equivalent circuit. There's our equivalent for this parallel component. That is, you found it to be 1.286 ampere times the equivalent circuit, that's 5 ohms. So that's about 6.429 volts, okay? So that's phi, let me see, phi parallel, okay? And this is the voltage drop that's going to be equal for all these resistors. So the potential drop here from this point to this point is also going to be 6.429. And the potential drop from here to here is also going to be the same. From here to here is also going to be the same. No matter how many like components you have in the circuits, it doesn't matter, okay? Potential drop is going to be the same, but the current is going to be different. Okay, so now we can find power directly by squaring this term and dividing by the 20 ohm resistance. That's the short way, or you can find the current, okay? So yeah, for this one, okay, let's go the easier way. Earlier I was saying let's go with current. It's easier to calculate power directly from this. So power across 20 ohm resistor is just V parallel square divided by R 20 ohms, okay? So that is 6.429 volts divided by 20 ohms. So that's about 2.067 watt, okay? So now you have the power, and this resistance is inside a block of ice that's at 0 degrees centigrade, okay? So whenever ice is melting, what makes it melt? So you have a ice that's at 0 degrees centigrade, and as it melts, it goes to water at 0 degrees centigrade, right? It's the phase transition, fast phase transition. So how much heat is supplied for this? That's mass of the ice times latent heat of fusion, right? And that the latent heat of fusion is given to you. You only need to find at which rate this mass is decreasing, the mass of the ice, Mi, okay? So that means, so if I took delta Q, so how much heat that I should supply, then I have to do delta Mi LF, right? Your mass is constant, so I can take that out. That is delta LF. I can do something like this. So all you need are no, your mass is not constant, it's changing. So it has to be delta M. Your LF is constant, so LF is a constant. Mass is not a constant because in this case, your mass of the ice is decreasing, right? And the mass of water is increasing. So it's happening at a certain rate. Okay, so all you need to find is how is this changing? So So if you divide both sides by time, because power is energy divided by time, right? Heat supplied over time. That is LF times till MI over time. So you're required to find this, right? So delta MI over delta T is going to be delta Q over delta T times 1 over LF. So delta Q over delta T is power, right? P20 ohm that we just found over 1 times LF. So this means it is 2.067 watt, 2.067 watt dot 1 over. So the value for LF, I think it's given to be 10 to the 5 joules per kilograms. So here I'm using everything in SI units, so my answer will also be in SI units. So I will get my answer as 6.19 in times 10 to the second minus 6 kg over second. But you're asked in gram per second, so that is you need to multiply this factor with 3. So 10 to the 3. So that's 10 to the 3 grams per second. So that's the rate in which the mass of the ice, okay, mass of the ice in that particular resistor 20 ohm will be decreasing. So do you have any question? Okay, let me look at the chat. Okay, no questions. Okay, so let's go to next problem in that case. Problem number 2. So it's a very challenging problem. Problem number 2. It's a cube that has like a resistor in all of its all of these edges. So suppose there is a resistor R along each edge of the cube. So there will be 2 resistors, and all of them are similar. Okay, so you need to find the equivalent resistance when you pass the current from point A to point B. So remember in the last problem, what I was saying was that if the current divides, then the resistors are in parallel, and if the current isn't dividing, that means the resistors are in series. Okay, so that is useful here as well. So let me draw the diagram first. Okay. Q2. And okay. Okay. And you also have resistance here. You also have resistance there. You have resistance there. Here. Okay. So yeah. So here's a rough sketch, and all of these resistors, they are R. So this is your point A. Okay. And this is your point B. So you're passing, let's suppose I current from here, then the current gets divided here. Okay, so since the resistors are like similar resistors are equivalent resistance, what happens is, well, whenever there is a division of current, it will just be divided by the number of resistance. So this branch will have I over 3 amount of current, this will have I over 3, and this branch also will have I over 3. Okay, so now this I over 3 current goes to this point, and like it will this current I over 3. Now it will be further divided into two branches. Here one branch, here is the another branch, okay? So I over 3 will now be divided by half, that is I over 6, and here will be I over 6, okay? And now this I over 6, so this I over 3 goes to here, this I over 6 comes from here, okay? Now this I over 3, it's also going to be divided like here. Here you have divided this I over 3 into two parts, right? This I over 3 will also be divided into I over 6 and I over 6, okay? Now this I over 6 coming from this side and this I over 6 coming from this, there is like coming from this side. And this I over 6 is going to this side, okay? So it's quite tricky one. So now you have, now you'll have, let me think. Okay, you have I over 3 here as well. So I did divided I over 6 for like this two currents. Now there's another one over here. This will also be dividing into I over 6. So here, if you look here, it will be I over 6, and it's going this direction will also be I over 6, okay? Now you have this and this currents going this direction and this direction. So at this point, you have I over 6 coming from here, I over 6 coming from this point, okay? And you have I over 6 coming from here, okay? Okay, now you have I over 6 coming from here, and this will also be I over 6. It goes, because there's I over 6 coming from here, I over 6 coming from here. Why is it not I over 3? So this has to be I over 3. Because I over 6 coming from here, I over 6 coming from here. So this is going to be I over 3. And you have I over 6 coming off from here. So this will also be I over 3, okay? And you have I over 6 coming from here. No, I over 6 coming from here, I over 6 coming from here, which will sum up to be I over 3 from here. So it's like, you know, symmetric. If you just imagine the current was flowing from this side, this will be I over 3. So it's the similar situation. So that's why it's a very challenging problem, because you need to think a lot. Okay. So now you're supposed to find the equivalent resistance, right? So use the Ohm's law. So you only have like two paths for the current in this case. If you look at like whichever path you choose, you'll end up with three currents. There's I over 3, I over 6, I over 3, and you'll reach to point B. If you go from here, you'll be selecting I over 3, I over 6, I over 3. So it's like, you know, there are multiple paths. There's 2 points, A and B, and there are like multiple paths. No matter how, you can go from any direction, but you'll reach at the same point, and the length of the path is same. It's not like this one is different, that one is different. It's same. So that means your potential drop across A and B, since all of these paths will be in parallel. So no matter if you go from this way, no matter if current goes from this way or this way, all of these are in parallel. So that means the potential drop across any of these paths will be just I over 3 times R, there's 1, plus I over 6 times R, that's this, and let's take only one path for now, and that will be I over 3 over R. So if you take this path, it will be the same, I over 3 times R, I over 6 times R, and I over 3 times R. If you take this way, it's also I over 3 times R, I over 6 times R. So it's just parallel, right? The potential drop across each of these paths, no matter from where you go, will be the same, okay? So that's your potential drop. So that will be 5 over 6 times IR. Okay, so if I reduce this diagram to this thing, just simple are equivalent, right? Your potential drop will be V, okay? That is V will be I times R equivalent. So that is I times R equivalent is 5 or 6 times R. I and I gets cancelled. R equivalent will be 5 over 6 R. So there's your equivalent resistance. And I don't know like if this kind of problem will be asked in your exam or not, but I think that it won't be because it's a very hard problem. So yeah. Do you have any question? Okay, let me check the chat. Okay.
So in general, we only needed to calculate the potential drop of one of those paths because it was equal.
Tomorrow, I think you'll be asked to find equivalent resistance, maybe not in like a complex way, like a complex problem like this. Sometimes like you'll be asked to do circuits like this. So sometimes you'll be asked to find equivalent resistance in circuits like this. I hope you have seen something like this before. Okay. So how do you find equivalent resistance? Let's suppose all of these are equal, even if they are not, it's not a big deal. So what if the current is flowing from here? The current is going to divide I, right? I1, I2. It's going to be I over 2, I over 2. So you can do it in a similar fashion like I did. Okay, but there is another way to do this. Okay, so another way is just doing it simply. That is, I just added a resist. So like this and this, it's going to be parallel. So you find the equivalent circuit for this part, okay? That is going to be R over 2, okay? If we do the 1 over R plus 1 over R thing, okay? And now your circuit will be reduced to this small thing, okay? And now you have 3 of these in series, right? Which is parallel with this one. So you have R plus 1 over 1, big 1 over R plus 1 over R over 2 plus 1 over R. Oh no, these are in series, sorry. I made a mistake. You have this thing in series, that means the equivalent resistance will be R over 2 for this 3 plus this will be parallel with this small r. So that means you have 1 over R plus 1 over R plus R over 2. And now if you further reduce it, you have this resistance, right? And another resistance. Okay, you can just like make this one like this. So you have R and resistance that is coming from here. Okay, let me call that R equivalent, and you just add those two because these are in series. So you can also do find the equivalent resistance like this. Okay. So let's go to third problem if you don't have any questions. Let me make it large. So I don't want this part because it's diagram from another question. So yeah, question number 3, I think it's a very important question for tomorrow, because there's Kirchhoff's voltage law. So it applies that, and it's very important. And I think there will be a problem based on this one. So let's do this. So you have 2 batteries, right? And there are 3 resistors, and you have like two two rooms, or I call them rooms, but you have like definitely, you can like, you need to make loops, and you need to solve the equations for those loops in order to find the EMF source. So what must be the EMF E? So that's the second battery's EMF. In order for the current through 7 ohm resistor to be 1.75 amperes. So you are given the current which is flowing through this resistor. So you need to find the EMF E that is needed for this resistor to have this much amount of current. So it's a hard problem. How to do it? Okay, let me draw that. Okay, so let me draw the diagram first. So you have a battery that's 24 volts. You have a 3 ohm resistor. Okay, you have another battery here. What's the EMF you don't know, and you need to find. It's 2 ohms. This one is 7 ohms. Okay. Okay. And you have current flowing here, so that's given to be I 1.75 ampere. So you need to find the E. I think this current is also given to you. Oh no, it's not given. So let me call it I. Let me call this one I1, this one I2. Okay. So how do you solve this one? So you make loops. So usually what I do is I make 2 loops, and from where like I can solve this one using Kirchhoff's law. So my first loop will be this one. So you have a from like, you know, the outer loop, the outer circuit, just the outer circuit. So if you make only the outer circuit, then it will be something like this. It's 24 volt I, okay, and you have a I here, and you have a 1.75 ampere here, 7 ohm. So although there is a segment here, like it seems like this same I is flowing here, but it's not so. So that's why I'm drawing something like this. Okay. So I'm not looking at here, and this will also be I. Okay. So this is I2. So this is my loop 1. Okay. And this is my loop 2. Okay. Let me draw the loop 2, only the loop 2 here. That is this. Okay, so this is 2 ohms. This is what we don't know. We don't know I1. We know that it's I2. This is 7 ohms and 1.75 amperes. Okay, so this is your loop 2. This one and this one. This is loop 1 and this is loop number 2. So now we'll be using the Kirchhoff's law in the first loop. Okay, so in loop 1, you have this battery, right? This is positive, this is negative, so current flows from positive to negative. There's I going in this direction, okay? And there will be a voltage drop across this resistor. Since current is flowing in the same direction as the loop is moving, it will be a negative, okay? If your loop is moving in the same direction, and if the current is moving in the same direction with the loop, then in that case, you have to take the voltage drop across this resistor to be negative. It's like, you know, there is water flowing and there is a pit in here, okay? And the water gets, like some water gets trapped in here. So not all the water can flow to the other direction. There is some drop. So that's why you need to minus this part with the total amount of water flowing or something like that. Okay, so you have a 24 volt, okay, and some of this voltage 24 volt got dropped in here. That's negative minus I times R, right? Potential is I times R, Ohm's law. So that is I2 times, let me call it R2, okay. And there is another resistor, which I forgot to make. Here's another resistor that is 3 ohms, okay. So there is also drop in this resistor, so that will be minus, let me call it R1. I'll call it R1 for now. Okay, let me call it R1, this one R2, and this one be R3. Okay, that is I, because I amount of current is flowing here, same amount of current leaving from the battery, I times R1, that will be 0. Okay, so that is 24 volts minus, what is your I2? That is 1.75 ampere times your R2 is 7 ohms minus, you don't know the value of I, so I'll leave it to be I. R1 is 3 ohms, that's 0. Okay, so if you solve for I, then you'll get 3.80 ampere. Okay, so this I here is 3.8. So if this is 3.8, if this is 1.7, then well, what will be this current? It will just be subtraction of this amount of current from this one. So your I1, okay, your I1 is going to be I minus I2. That is 3.8 ampere. That is this current subtracted by this. Okay, 3.8 minus 1.75. So this is going to be 2.05 ampere, and that's the amount flowing in here. Okay, so now look at loop 2. So you have your unknown EMF. You already have found I1. So now in loop 2, if you apply the Kirchhoff's law again, what you'll be doing is your E, you have EMF E, okay, and you have a drop. So current is flowing in the same direction as the loop here. So it will be negative I2 times R2. This is R2. And minus or plus. Okay, here it's I1 is in this direction, right? I1 is flowing, and your loop is going in another direction, in this direction. So current is flowing in opposite direction. So you need to take it positive. So that is I1 times R1. Or is it? Or it's R3. So I'm writing it to be R3. So this is going to be R3. Okay. This is 0. So that's E minus your I2 times R2, that is this thing, 7 ohm times 1.75 ampere, 7 ohm times 1.75 ampere, okay, plus, what's your I1? That's 2.05, and R3 is 2 ohms, which is 0. So if you solve for E, so E is going to be 8.6 volts. Okay, that's your EMF. You can also choose this one to be your loop 1 and do it, but that's going to be a lengthy process. Okay, but it will give you the same answer. If you choose loop 1 to be this and loop 2 be this, or loop 2 to be this one and this bigger outer loop to be loop 1. You can choose any loop you want. but this is the general trend. So that's your unknown EMF. Do you have any question on this one? Okay. Let me look at chat. What about 3 ohms? Where? So I took the 3 ohm when I was taking loop 1. So if you look at loop 1, I've already addressed 3 ohms here because it comes under the loop 1. I'm taking this outer loop to be loop 1, right? But in the second loop, you don't have a 3 ohm. You only have 2 ohm resistor and you have 1.75. You have a 7 ohm resistor. That's in loop 2. So yeah, if you have any other question, you can interrupt me at any time. Okay. So this is a very important question. Question 3 is to practice some of these questions before going to exam tomorrow. It's very important. So let's look at problem number 4. Okay. So you have cell membrane, which can be modeled as a capacitor. You have a positive at like one of the outer membrane to be a positive and inner membrane to be negative. And whenever you have charges that are separated, positive and negative charges separated at some distance, there is a potential generated. Okay, that's capacitance. Basically, you have like electric field in between that, which stores the energy. Okay, so it's a capacitor as like a cell membrane as a capacitor. So there's a model that the scientists do when they do biophysics. So now you need to find what is the capacitance per square centimeter of such a shell wall, and you are given the dielectric constant of about 10. So let's solve this problem. Okay, it's not a hard problem. It's just could be hard to understand for some of these students. Okay, you have a plus charge outside, and you have negative charge developed inside, right? And this distance, that's 7.5 millimeters, so it's very large cell membrane. Usually you want to find such thick cell membrane, I guess. And axon, so this is the axon. So it's a NORP cell. I think it's a NORP cell where you'll find axon, okay? So whenever you have charge separated at some distance, you have capacitance, and your capacitance, the most important formula to find capacitance is epsilon naught, epsilon sub 0, A over D. A is the surface area, okay? That's the area of this plate or cell membrane. So whenever you have capacitor, you have two parallel plate capacitor. Whenever you have two parallel plate capacitor, you have two plates, right? And those have areas. That is A, okay? The area. And D is the distance between the two capacitor plate. So D here will be this, 7.5 millimeter. E0 is what you say, like it's the dielectric constant for vacuum or air, okay? It's not, that's because like what dielectric constant means is it's the epsilon multiplied by some factor, okay? So this constant means how much times this media has more dielectric power than vacuum, okay? Your vacuum or air has E0 that you have always been using to find the capacitance. But whenever you have other media, right, if you use some kind of gel, like a gel which can transport charge, you have like a dielectric media, okay, that has like a certain times higher dielectric constant dielectric like this epsilon 0 than the vacuum, okay. And so this factor, ER, is 10, given to be 10 right now. So usually the formula for capacitance, general formula is, K times, some represent it by K. So yeah, K A over D, and K is E0 times ER, okay. And ER is given to be 10 here. Okay, some represent this ER to be K, okay. So I'll just write it K times E0 times A. So what this K means, the direct constant in, means that this media which is inside this two plate is like has more dielectric power than vacuum, and that's 10 times higher. So dielectric power means for the power to separate positive and negative, okay? So that's dielectric property. So that means your capacitance will be 10 times E0, that's 8.85 times 10 to the negative 12 farad per meter, times your area, that's going to be, so since you are finding it for 1 centimeter square, because the problem asks you to find it for 1 centimeter square, you'll be taking 1 centimeter square as your area, okay. So when you convert 1 centimeter square into your area, okay, let me write it 1 centimeter square, that will be 10 to the negative 4 meter square, okay, divided by d distance, that's this 7.5 times 10 to the negative 3 meter, okay. So if you do the calculation, you'll get this much amount of capacitance. So 10 to the negative 6, you can write it as a microfarad, so 1.8 microfarad, okay. So that's the capacitance per centimeter square for 1 centimeter square, right? We're using 1 centimeter square as the area, okay. So that's part A for this problem. For part B, you need to find the electric field that's being stored here. So a capacitance, what it does is it stores the energy in the form of electric field, okay? So that electric field is given by the potential difference, right, divided by the distance. So, and I think the potential difference is in here. If you read the problem, it's given to be 85 millivolts, okay. So if you take that, that is 85 milli means 10 to the negative 3 volts divided by the distance, that is 7.5 times 10 to the negative, oh, I took it to be 3. So it's nanometer, not a millimeter, sorry. There's a nanometer, yeah, now it makes sense, because a millimeter is very large for biomembrane. Okay, so meter, nano stands for -9. So if you do that, you'll get 1.13 times 10 to the 7 volts per meter. See how large the electric field is, even though this structure is very small, okay? So that's why like the electric field like generated in the biomembrane, they are so high that they are like able to like move the, even the electric field is sometimes the potential generated between the two layers are powerful to make the ion transport a few times. There are like ion channels. I mean, you might know more than I do, but there are like opening and closing of the channels, right, to balance the salts so that the usual nerve functioning works. Okay, there's the electric field. So it's very high. Okay. Any questions? No, I can't hear you. I guess you are muted. Never mind.
Are you able to hear us talk?
No, I can't hear you, Hannah.
Was that a no? Okay.
Don't know why. Maybe I'm muted. No, maybe I need to increase the volume. Okay. I don't know why I can't hear. Okay, so if you have any questions, please feel free to write in the chat. I think I'm not hearing the audio from you guys. Don't know why. Okay, so problem number 5. Okay, so it's a capacitance problem. There are multiple capacitors here. So what you need to find is you need to find the equivalent capacitance between point A and B. And you need to find the charge that is stored by all of this system combined. And you'll also need to find the charge that is being stored by 6.5 nanofarad capacitor and the potential drop across 7.5 nanofarad capacitor, okay? So, okay, let's do this one. So this is number 5. So let me draw the circuit A, B. This is capacitor. Here's another one. Okay, and you have another one here. So this is 7.5 nanofarad, 5.29 nanofarad. This is 6.5 nanofarad. Okay. Okay. So you can convert this circuit into this thing, like I did for the resistor, right? That is the equivalent. All these three are in parallel. So for capacitance, it's very easy when capacitors are in parallel. You just add those three. Okay, so the formula is just opposite to the resistors. So if it was resistor, you need to do 1 over R1, 1 over R2, plus 1 over R3 if they are in parallel. Okay, so here's just summing up all these capacitors. That's this and 6.5 nanofarad. So that's 19.2 nanofarad. Okay, that's the equivalent capacitance, which the first part asks. So let's go for the second one. You need to find the charge. The total charge stored will be CQ times Q, that's C equivalent times CV, okay? That is the voltage across these capacitors. So it's going to be the same because they are in parallel. So your C equivalent is 19.2 nanofarad, and I think it's given to be 25 volts. That is the voltage across the point A and B. So that's going to be 25 volts. So if you do this, so all I can do is I don't need to touch this nano, right? So what I'll do is I'll just multiply 19.2 and 25. So that will give me 482.35. And I'll just write it to be nanocoulomb, okay? That's easier for me to write it in the form of nanocoulomb. Okay, let's go for C. You need to find the charge stored in 6.5 nanofarad capacitor. That is this one, okay? So that is Q 6.5 will be the capacitance of 6.5 times the voltage across that 6.5 capacitor. So your capacitance is 6.5 nanofarad, right? And the voltage drop is going to be same across all of these capacitor because they are in parallel. So it's going to be 25 volts. Okay, so that is 25 volts. So if you multiply it, it's going to be 162 nanocoulomb. Okay. Okay, so the last problem is, I think, what is the voltage drop across 7.5 nanofarad capacitor? Let me double check that. Okay, yeah. So you don't have to solve anything because, like I told you, it's in parallel. So the potential drop will just be the same. Okay, 25 volts. That's the answer. Because all of these are in parallel. So the potential drop across this and this, or this and this, this and this, or this and this, right? So it's going to be the same. Okay. Let me read the chat. Okay, so if you have any question, drop it in the chat and I'll have a look. Okay, so yeah, in problem 6, you have the RC circuit, and I'm not going to do it because yesterday only I heard from Professor Fabi that you won't be asked RC circuit, okay? But you can go ahead and solve this. I will write the answers for you. For part A, the charge Q2 will be 22.5 microcoulomb, okay? And for part B, the resistance R1 will be 31.6 ohm. So it's a similar situation like I did in a random problem that I generated here when I was finding the equivalent resistors. So you can find the equivalent capacitance first and do that like I did here, okay? So here it is only the resistor, but if I replace this part with capacitance, then it will be the identical circuit. So all you need to do is you need to find the equivalent capacitance when there is capacitance and equivalent resistance when you have resistors. Okay, that's how you do it. And the same concept, the potential drop will be similar. If it's in parallel, it will be different if it's in series, okay? That's how you do question 6. So I'll jump to question 7 for now. So let me double check that. Any question? Okay. Okay, so for question 7, you have a point charge placed at each corner of the square with side length A. So you have a equal, like they are separated by equal distance. 2 of the charges are positive, the top one, and 2 of them are negative. What is the direction of net electric field at the center of the square due to 4 charges? And what is its magnitude in terms of Q and A? So there could be values in the exam. So this is an important problem. So you might be asked a similar problem. Okay, so practice a few of them before going to exam tomorrow. So you might be asked a triangle, you might be asked like 3 charges are here and need to find electric field at this point. Okay, so it's not a very hard problem. So you have 4 charges, plus Q, minus Q, minus Q. And this is the center. The distance is A and all of these sides are equal, right? So you need to find the net electric field, the direction as well as the magnitude. E, let me write it O, add O, already. Like this. So you need to find the magnitude as well as the direction, okay? So let's do first part. Okay, so if you only look at the top two charges for once, so for now, let me only take the above two charges, that is plus Q and plus Q. Okay, and let me draw it. So if this is your center, okay, you'll have electric field here due to this charge and this charge, right? And where will be the direction? It's a positive charge, so the electric field will, at this point, will, due to this charge, will be away from this place, because positive charge, they emit the electric field, right? And the negative charge, the electric field enters the negative charge. Okay, so keep that in mind. That matters here. So due to this particular charge, your electric field will be to this direction. Okay, and due to this particular charge, the electric field at the center, there's the O, will be to this direction. Okay, let me write this to be A, this to be B, this to be C, and this to be D. So that's, it's A and B. So let me write to be EA, this to be EB vector. So now what you are doing is you are finding the resultant of these two vectors. So how do you find the resultant? If you know the parallelogram law, what you do is you draw a parallelogram, right? And you use the parallelogram law. Since these two charges are equal and this distance is A, this is going to be a 90-degree because the diagonals of a square, they intersect in a 90-degree. So this is a right triangle, right? So whenever you have a right triangle and this, both of these sides going to be equal because it's a square. So that means this side will be A over root 2, this will be A over root 2, right? Because if you square and sum, it will be equal to the hypotenuse, right? Because if you square this, A square over 2, then this will be plus A square over 2, and if you take the square root, that will be 2A square over 2, 2 to cancel A, and that's equal to the hypotenuse. So it satisfies the Pythagoras theorem, okay? So this distance from here to here, there's A over root 2, and also this distance, it's going to be A over root 2, okay? Now, how do you find electric field at a point due to a charge? So electric field due to this charge at B, it's going to be K, right, times Q, that's the magnitude of the charge, over the distance, that is A over root 2. Okay, so my A and Q are very similar looking, so I'll write A like this, okay? A over root 2. Okay, so that is root 2 K Q over A, okay? And if you find it for, so electric field at this point due to this charge EB is this in magnitude, and your EA will also be the same, right? Because there's same charge, same distance, it's just the direction that is different, but the magnitude will be the same. So it will also be root 2 times KQ over A. Okay. Okay. So what will be this resultant vector E? Resultant. E resultant 1. I'll write it to E resultant 1. Okay. So whenever you have two vectors, since this angle is 90 degree, this angle also will be 90 degree. These are vertically opposite angles. Like you have two angles. If this is 90, then this is also going to be 90, right? So the angle between two vectors is 90 degree. Whenever you have two angles that are 90 degrees, your resultant is just going to be the sum of the two, okay? There won't be any cross terms. So you can just add them. So your E resultant 1 will be EA plus EB. So the magnitude is just going to be the regular sum. That's 2 root 2. Okay, let me do A plus root 2 KQ over A, right? So that's 2 root 2 KQ over A. Okay, so that's your first resultant due to the top one, but this is not the final answer. You also need to take account of this too. So here we won't be talking about any interactions between these charges. We're not dealing with the force here, okay? We're not dealing with the interactions between these charges. We're just trying to find the effect of these charges in the center, how the net electric field here will be, okay? Just the influence. So you can do it like independent of the other charge. You don't have to like take any cross terms like in the force. So now if I took the bottom one, so if you took the bottom one, so you have negative Q, right? And you have A, and your center is here. The distance will be same, A over root 2. Okay, just like, and the angle will be 90 degrees. And your vectors, this is C, this is D, right? Your EC. Oh, this time it won't be going to that side because it's a negative charge, right? So it will be coming to this side. It won't be going to this side because it's a negative charge. And remember, negative charge, the field enter the negative charge, okay? And for this one, it will be towards this side. So it's EC vector, and this is the ED vector. So the resultant, okay, resultant of these two vector, maybe it won't be this long. So this is going to be the E resultant 2 due to the EC and ET. Okay. And at first, let's calculate the magnitude of EC. So magnitude of EC is going to be the same like in the last case, that's KQ. So we won't be taking the negative sign here, okay, because we're only dealing with the like magnitude over A over root 2, right? So that is going to be root 2 KQ over A, right? And this will be equal to the ED. So your ED, that's this due to, okay, that's due to this charge. This minus Q charge will also be the same, root 2 KQ over A. Okay, now if you find the resultant, your resultant will be EC plus ED for magnitude, right? So it will also be 2 root 2 KQ over A. So you have E resultant 1, 2 root 2 K over KQ over A, right? And you have resultant 2, there's also K root 2 root 2 KQ over A. So the net resultant will be the sum of the two because both are pointing downward, right? You have this as an origin. You have E resultant 1 that's going in this direction. You also have E resultant 2 that's also like directly over the same vector. Whenever you have two vectors going in the same direction, you can just add them up like a scalar. So your E will be E resultant 1 plus E resultant 2, right? Let's only do the magnitude. That is 2 root 2 KQ over A plus 2 root 2 KQ over A. So that is, it's the same term. So 2 times 2 root 2 KQ over A. That is 4 root 2 KQ over A. So that's your E resultant due to all of these four charges. And the direction here will be downward. Downward, right? Directly downward. So if I write it vector, this is the direction, okay? So this is how you solve this kind of problem. Do you have any question? Okay. So if not, then let's go to the last problem. That is problem number 8. Let me open the problem first. So this is problem 8. So you have an electron that is projected with an initial velocity of 2 times 10 to the 6 meters per second into a uniform field between these two parallel plates. Okay. Assume that the field between the plate is uniform, so this electric field, it is uniform and vertically downward, like the arrows are pointing, and the field outside the plate is 0. Okay, so there isn't any electric field outside which is influencing this electron that's moving. Okay, if the electron just misses the upper plate, so if it moves and it misses the upper plate, so it just grazes this edge. Okay, but it won't. Misses the upper plate as it emerges from the field. Find the magnitude of the electric field. So you need to find this E. Okay. And suppose the electron in this figure is replaced by a proton with the same initial velocity. What would the proton hit the plate? So will it hit the plate or will it not hit the plate? Okay, and in part C, you need to compare the trajectories of these two and their differences, and you'll also need to find whether the gravity affects this proton or electron or not. Okay, so it's a very good problem. Okay, so you have this plates, there's 2 centimeters in length. Okay, you have another plate and you have electric field going in this direction, right? This is the electric field. This is the electron that goes in here and it grazes. Okay, goes to that direction. Your initial velocity is given, that is 2 times 10 to the 6 meters per second. Okay, and you are given this thickness, that is T, so D is 1 centimeter. Okay, so how do you find the electric field? So it's like a projectile problem. You have a projectile that you threw, and every time there is a gravity that's pulling it down, okay? Force of gravity that's pulling it down, and it falls in a parabola. It's similar to that. You have like electric field that has force which makes it to get attracted to this upper plate. So how do we do this? So you need to use the kinematics because you are given the velocity and you have distances here, okay? So you have this this vertical distance traveled. So this is the distance covered in y-axis by the electron, right? That is half of the 1 centimeter. So vertical distance covered here is, let's call it y, that is 1/2 centimeter, that is 0.5 centimeter by the electron. Okay, and okay, so now you use the kinematics. So which equations to use? So you need to find the electric field. So let's at first determine which equation to use to find the electric field. So you know that electric field is force experienced by a unit charge, okay? So that means electric field is mass of the charge times the acceleration of the charge, right? Divided by the charge itself. So yeah, so that means if you have the mass already, right? It's the electron. So your mass of the MQ is mass of the electron, that is 9.1 times 10 to the negative 31 kilograms, right? And you have the charge that Q is E, that is basically 1.6 times 10 to the negative 19 coulomb charge. So you have both of these things. All you need to find is the acceleration, okay? That is constantly putting this charge towards the upper plate. Okay, so if I want to find the acceleration, that means Q over MQ times of electric field is the acceleration, right? Okay, so along Y, so now if we use the kinematic equation along Y, so you have these splits, you have the electron here, and it travels like this. So the vertical distance traveled is 0.5 centimeter, right? So along Y, this is plus Y direction. You have a kinematic equation. If you use this equation, that is V0Y, initial velocity times T plus half acceleration Y T square. And this acceleration will be equal to this, right? This is AY. That's the vertical acceleration, which is pulling the charge towards the plate. So, and what's the time? How do you find the time? So you can find the time. Let me write this equation 1. If you do log x. So if you look at log x, you have a range of that projectile given to you. This is the range, right? It started from here, it landed on here. So you have this range 2 centimeter. That is, you have the horizontal distance and you have the velocity, horizontal velocity. This is V0x, that's 2 times 10 to the 6 meters per second. So if you do along x, your basic equation will be x, that's the distance traveled, let's call it x. That is initial velocity times t plus half a x t squared. So this is different acceleration. It's the acceleration in x, and since it's like a projectile, you don't have any forces acting in x direction. You don't have any forces in x direction. This quantity will be 0 because you don't have, when you don't have a force in x, you don't have any acceleration. So you only end up with V0t, like in the case of projectile, right? When you have a projectile that you throw, you don't have any x acceleration, you only have the y acceleration. That's the acceleration due to gravity. It's similar to projectile. So what is your time? T is x over V0. So what is your x? That is 2 centimeter. 2 times 10 to the negative 2 meters divided by V0. That's 2 times 10 to the 6 meters per second. 2 and 2 cancel. That is 10 to the 4 seconds. Oh, no. 10 to the negative 8 seconds. Because when this positive goes up, it's going to the negative. So that's your time of, I would call it time of flight that the electron had. And this is same as this time, because in the same time, the electron also traveled this vertical distance of 0.5 centimeter. Okay. So we're going from here to here. So your y is, so you're trying to find the acceleration, right? So your acceleration ay is going to be, this term is going to be 0 because you don't have any vertical velocity at the beginning. It's the v0, 0 means initial. So it's going to be, maybe do half ayt square, okay? So that is your acceleration. Ay is going to be 2y, 2 comes that side, over t square. And you have your y to be 0.5 centimeter, that's 10 to the negative 2 meters, divided by t squared, that's 10 to the negative 8 seconds square. So if you calculate the ay, okay, it seems I forgot this calculation, so let me do the calculation in my calculator real quick. 2 times 0.5, 10 to the negative 2 over 10 to the negative 8 square. So that's about 10 to the 14 meters per second square. So it's a very high acceleration. See how greater it is from the acceleration due to gravity, 9.8 meters per second, right? So do you think the gravity will have effect on it? That's the last part of this problem. Okay, so you have the acceleration, and you know the acceleration is this. So let me write that. Let me write E in the form of acceleration, that is AY times M over Q, since AY is Q over M times E. Okay. Okay. So what is your AY? That is 10 to the 14 times mass of the electron over charge of the electron. So that is 9.1 times 10 to the negative 31 kilograms, and divided by 1.6 times 10 to the negative 19 coulomb. Okay. So let's not write it to be the vector. We're only concerned about our magnitude. So it's going to be 5680 newtons per coulomb. So that's the electric field. Okay. Okay. Yeah. Now that you have found the electric field, I think the part B asked about what if this thing was not the electron, it was, what if it was a proton? Okay. So I don't know if you know the Fleming's rule or not, but if you use that, the proton has same charge, but it's positive, right? It has same magnitude as electron, the magnitude of the charge, but it's a positive charge. The electron is same charge, but it's negative charge, right? So the direction it's just going to be downward, right? But we don't know if it's like going to be like this or the trajectory is going to be like this, but we know it's going to be downward. So because it's a negative, it's a positive charge. That's one conclusion. But to find whether it will hit the base of the plate or not, what we can do is we can calculate the Y for the proton. So YP is going to be half, right? Let me do it, V0Y T square plus half AY T square. So let me write it prime so that we don't get it confused with the acceleration that the electron had previously. Okay, the velocity was same for both of these. So the time is also going to be different. Okay. Will it be different? Let me double check if the time is going to be different. No, the time is going to be the same because it's not involving any mass or charge. Mass and the charge of the proton is different. Okay, so the time is going to be the same. Okay, so this part is 0. Is it 0? No, it's not 0. Oh yeah, initially it's 0, so because it's not going towards y direction. So sorry about that. So it's going to be 0, right? So this is also half AYT square. That's Y proton, okay? So how do you like find YP? So if you look here, if you find the electric field for the proton, right? So we can find actually the acceleration for the proton. So A proton, AY for proton, it is going to be, so it is like Q proton divided by mass proton times the electron, electric field, right? Electric field is going to be same whether it's proton or electron because we're not changing that. Okay, if I divide it with the AY of the electron, right? If I divide this whole term with that, then that's the Q of electron, mass of electron, and electric field. E and E are equal. Also, the charges are equal. The magnitude of the charges are equal, right? You don't need to take this negative sign for both of these. So the acceleration per proton is just going to be a mass of electron divided by mass of proton. And proton is 1836, so it's 1836 times heavier than the electron, okay? So that means your YP for proton, YP is, so since the acceleration for proton is less than, it's going to be less than that of the electron, your YP for proton is going to be less than that of electrons. So what does that mean? This is the deflection, right? This is the distance. This is this distance, right? This distance. So it's going to be less compared to that with the electron. So as it passes this line, so if the plate is up to here, it will have less deflection. So that means for proton, the trajectory will be something like this. It will be a long trajectory, unlike the electron, which had trajectory like this. Okay. Okay, so that means it won't hit the plate. Okay, proton. Okay, so there's a challenging problem. So I don't know, like this much complex questions will be asking your exam, but it's always good to have knowledge at this depth. Okay. And this is like a university level questions. Okay. So the last part, I think I have already solved it. That is the acceleration due to gravity, it won't have any effect because effect as acceleration, the magnitude of the acceleration is in the order of like 10 to the 14 meters per second, as you saw earlier, which is very, very greater than 9.8 meters per second square. So that means force due to gravity is going to be very small compared to the force due to the electric field. So it won't have any effect. Okay. Do you have any questions? Let me turn this up, stop this here. So if you have any question, please feel free to ask me. We can try unmuting once and trying, maybe it works. If not, then you can type it in the chat. If not, then yeah, have a good night. We've finished the program quite fast today. Thank you for coming.